Alright, my name is Ronak Patel, and this is my lab report on the motion of a falling object. The purpose of the lab is to quantify the motion of a falling object as the motion is affected by gravity and drag force. First, the effect by gravity was considered and analyzed, and then the effect by gravity and the drag force was considered. Newton's second law of motion was applied to understand the effects from both. A baseball was dropped and the motion was analyzed with tracker to receive experimental data, and modeled using VIDLE to receive computational data. The experimental model and computational model were then compared to reveal that there was a net force acting on the baseball and that the object reached a terminal velocity during the motion. In this lab, two forces are adding up to be the net force. So the net force in this lab is non-zero. So in reference to Newton's second law, the final velocity will not equal the initial velocity because this component of the principle will not be equal to zero. So the weight force is the force that pulls the object towards the earth. The object is in free fall, so the direction is downward along the negative y-axis. The equation at the bottom is a representation of weight in coding form that will be useful later in the presentation. The other force is the drag force, the force that pulls the object away from earth. It is caused by the resistance of air. As the object falls, the air beneath pushes on it to slow it down. The faster the object is moving, the more the drag force. Now in the equation, B is the drag coefficient associated with the surface area of the object. The larger the surface area, the more drag force. This is the video of the baseball falling in the negative y direction. The plots are plotted on the graph here, and the graph turns out to be curved for a while, meaning there is acceleration. Then the slope gradually becomes constant, indicating the absence of acceleration as terminal velocity is reached. Initial position and final time was taken from the table to use for the Lab 2 start code. The ball's mass is indicated in the code here, and along with the gravitational constant, Newton's second law is applied with the following equation as we learned about in Lab 1. When the code is ran, with the weight force being the only force yielding to the net force, the following model appears. The model's prediction is not the same as what occurred in the experiment. The baseball moved less than what the displacement was supposed to be according to the model. Due to this discrepancy, the model overpredicted the results. However, the reason for this difference is because the weight force was not the only force acting on the ball. The drag force was also acting on the ball, as mentioned earlier in the presentation. Drag force is then accounted for in the code by using the turbulent force equation, which consists of the constant b and the baseball's velocity squared. The drag force equation is indicated here in the code. The b value 0.036 was determined by trial and error by matching the experimental final position with the model's final position. This is a much better representation of the baseball's falling motion. The drag force is the blue arrow, and the weight force is the yellow arrow. Notice the drag force started small and gradually increased. In the following comparison graph, the model of the weight and the drag force is closer to the experimental motion of the baseball, meaning the experiment was relatively successful. The model with drag force and weight falls slower than the model with weight only, as it has a slower velocity due to the drag counteracting the weight force. The small difference that separates the experimental line and the model line can be due to experimental error and slight video distortion. Overall, the model could have matched up closer with the experimental position if I angled the video better and ensured the baseball fell in a straight line. Other errors include human error by not having an exact B constant value. There also could have been more data points to increase the accuracy. Alright, now let's answer the lab questions. In response to the what does it mean question, the model that takes into account the weight and the drag force is better for displaying terminal velocity. This is the velocity versus time graph for the model with drag and gravity. Terminal velocity is reached when the amount of drag force is equal to the downward gravity force. The net force is zero, so the terminal velocity is the final constant velocity. As you can see in the graph, the line begins to level off to a constant value, indicating the terminal velocity. Now, in response to the what if question, if the baseball was thrown down with enough of a force, then the baseball would have a drag force that exceeds the gravity as shown here. However, eventually F net will equal 0 and terminal velocity will be reached as shown here. To get the graph, in the code, the force to give a velocity of -10 meters per second was chosen because it exceeds gravity. I also made it plot the velocity versus time graph with the following line of code. Here and here. Terminal velocity is the same because it is only dependent on mass, surface area, and density. None of these variables changed, so it is the same. This concludes Lab 2. Thank you.